Hi, doing a quick little video on related rates. Oh yeah, it's our good friend related rates, calculus, gotta love it. All right, check it out. So here we have some strategies I want to briefly go over with you before we even start looking at problems. The first strategy is identify all the given quantities and label with proper notation. Is it dv dt, the derivative of the volume? Is it the derivative of some speed? Is it the derivative of some x value? Is it derivative of some y? Most of these are all relatable to the derivative with respect to time. So that's why we need to learn and use implicit differentiation when we have the situations. So we're going to label them properly. Okay, that'll be a big help, and we got to start getting in our minds right away. How do we label? And we've talked about that in class and other areas where we need to make sure that we have the values labeled. So then as we go and apply and resubstitute items in, we know exactly what we have. Okay. Then we're going to write an equation involving the variables, right? Sometimes it might be a volume. Sometimes it might be an area. It could be other things where we have these known equations, a cone perhaps, or a cylinder. So we need to know some of those basic equations and whose rates of change are given or are to be determined. So then we're going to use the chain rule implicitly. So what that means is we're going to continue to take the derivative of some variable, but then we're going to tack on, if we're taking the derivative of the radius, for instance, then we would tack on multiply by dr dt. So that's what that chain rule implies. Okay, that's the implicit chain rule. So both sides of the equation with respect to time. Then we're going to substitute given and resulting values into the equation and solve. Okay. So here's our first example. Dun-dun. It is a spherical balloon that is being pumped up. Someone's pumping up a spherical balloon. And at a rate of 4.5 cubic feet per minute. Okay? And it says find the rate of change of the radius when the radius is 2 feet. All right, so what are we looking at here? One is we have to identify the information. So we've got a spherical balloon. So equation of a sphere, I need that. Volume is equal to 4/3 pi r cubed. Okay, so that's the equation of the sphere. So I'm going to use that somehow. Then it says a rate, it's blowing up at a rate of 4.5 cubic feet per minute. So every minute, another 4.5 feet is added, and it's growing spherically. Okay? That's a rate of change. Find the rate of change of the radius. So we want dr dt, right? Find the rate of change of the radius when the radius is 2 feet. So when r is 2. Well, what else do we know? We know that the volume is changing at a rate of 4.5 cubic feet per minute. So dv dt is 9/2. So put it in fractional form to make the math a little easier. So we don't know dr dt, and we know r though. We want to know, hey, when the radius is 2, what is that volume going to be, or what is the rate of the radius? What is expanding at? So we set dv dt because that's the volume. Took the volume here, plugged it there. dv dt. 4/3 pi. Well, those are constants, so we don't have to do much with them. Then we take the derivative with respect to r cubed. We bring the 3 down, and that becomes r squared. Well, then what do we notice? Oh, look, these 3's can cancel. Boom, because they're in inverse relationships, so we can cancel them. So we are left with 9/2. We're going to substitute some information in now. 9/2 dv dt, 9/2 is equal to 4 pi r squared. We have to tack on the dr dt, just like we did here, because we're taking with respect to r, we're taking the derivative of r, but with respect to t, and that's so that's going to imply that we need to take the chain rule here and utilize dr dt to symbolize that is being done. So now we can divide 4 pi r squared by 9, and that'll single out or isolate dr dt. We get 9 over 8 pi. We're going to plug in 2 now because we're ready to solve. Plug our 2 in. 2 squared is 4. So we get 9 over 32 pi, which is 0.09 feet per minute. Okay? So we notice the volume was feet cubed per minute, but as we're doing a linear radius, it's just feet per minute. Okay? All right. Second one. Let's take a look at this one. We got a plane, and it is flying overhead. So an airplane is on a path that will take it directly over a radar station. The distance s is decreasing at a rate of 400 miles per hour. So as the plane is going, the distance is decreasing. So it's decreasing at a rate of 400 miles per hour when s is 10. So right here, when s is 10 miles, what is the speed of the plane? Now they gave us this picture, so it's a big help to have the picture. Otherwise, just with those words, it would be hard to tell kind of where to draw it. But we look at distance from where a plane is to a building more on a linear sense as opposed to the direction in the x and the y. So this will always be the hypotenuse where that distance is changing. So what we want to do is, what do we have? And they also gave us this 6 miles is in the air. The plane is in the air 6 miles. And so we have a relationship. We have a right triangle. We have 6 miles. We have s is 10. But we don't know x, right? It says, what is the speed of the plane? Well, the speed of the plane is going to be determined by that x value, right? So we're going to need to take the derivative of something with respect to x of time, because speed is direction and time. So here we go. We're going to use the Pythagorean theorem to solve in terms of x, because we don't know, we don't have a value for this x yet. We need it. So we're going to find out the position of that x so we can use it later. So x squared plus 6 squared is equal to 10 squared, because 10 is there, 6 is there. So we'll get x is equal to 8 after we take the derivative, or not the derivative, excuse me, but move the 6 to the other side, and then take the square root of both sides of the equation. We'll get x is equal to 8. All right. Now, we have x squared plus 6 squared is equal to s squared. Now, that's what we want to use to find the derivative. Let's take the first derivative. So we'll take the derivative with respect to x. That's following one of our rules. We might have to differentiate to 2 different variables. And we do each so with the chain rule. So we take the derivative with respect to x here. And we get 2x. Remember to tack on dx dt, because we're looking for a rate of change in the x direction. Right? The plane was flying. We want to know what the speed is of this plane. Is equal to, bring the 2 down, that's 2s ds dt, right? Because this is some rate of change in this s. So imagine this, we have this, and so the plane is coming, so as this changes, then this is also changing, right? The hypotenuse is changing, and the x value is changing. So we have 2 things changing at one time. And so after we solve for dx dt, which we do because we want to know the rate of change in the x direction, is equal to s, there's the s, the 2's cancel, right, the 2's go away, s over x times ds dt. Now, we can do that. We get dx dt is equal to, we substitute the information in, we know that s is 10, that's what they gave us. 8 we found, right, the x is 8, that's what we found. And they told us that it's the plane is at a decreasing at a rate of 400 miles per hour. So here's our rate of 400 miles per hour in this hypotenuse direction. So when we multiply these, we will get negative 500 miles per hour. Now I know you might be thinking, oh, negative, does that mean it's slowing down? No, we can actually take just the absolute value of that and get 500 miles per hour as our result. Okay, and that is the change with respect to x as the plane is flying 500 miles per hour. All right, thank you very much. Hope you enjoyed that. That's related rates. Have a great day. We'll talk to you soon.